In this lesson, we will learn about how to identify the types of intermolecular forces between molecules and also discuss some of the properties that can be compared using intermolecular forces. Now, first we must distinguish between intramolecular forces and intermolecular forces. Intramolecular forces are the forces within the molecules. So they're the ones that are holding atoms together in molecular compounds, the ionic bonds and the metallic bonds. So those hold those types of molecules or compounds together. The intermolecular forces are the forces between molecules. And there are three different types: London dispersion, dipole-dipole, and hydrogen bond that we will discuss. Ion dipole forces will help us to explain some properties. Now, the order listed above, London dispersion, dipole-dipole, and hydrogen bonds, are the order of increasing intermolecular forces. So London forces are the weakest, and hydrogen bonds are the strongest of these three types of forces. Now, how we'll present them to you in the note is from the easiest to identify to a little bit more difficult to identify. And that's the progression that I've chose to present them to you. The first type of intermolecular force that we'll look at is the dipole-dipole force. And this occurs between two polar molecules. If you draw a molecule of CO, you'll see that there is a triple bond between the two atoms. There's a lone pair on the carbon and a lone pair on the oxygen. If you check the difference in electronegativity between these two atoms, you'll see that there is a polar bond between the two atoms, with the dipole pointed towards the oxygen because it is the more electronegative out of the two. Now, this is the molecule properly labeled with its dipole, but in order to look at intermolecular forces, we need to look at another carbon monoxide molecule beside it. So these are polar molecules, and where the intermolecular force lies is it's the force between the molecules holding them together in a sample. As you can see, the dipole on this molecule is slightly negative here, and on the neighboring molecule, it's slightly positive. So there's an attraction between the dipoles of the molecules, and that's where the intermolecular force lies. I'll use the short form IMF for intermolecular force, and this is a dipole-dipole attraction, or dipole-dipole force. Now, there are two diagrams here to show you how we might see these kinds of forces arising in a sample. This one on the right would represent a solid where the molecules are very orderly, and as you can see, they've aligned dipole to dipole to achieve maximum attraction and minimum repulsion. If you're looking at something like a liquid, the molecules will be a little bit less orderly, and there'll be a series of attractions from the negatives to the positives and repulsions from positive to positive or negative to negative. But overall, there are many intermolecular forces within the many molecules in a sample. We use a dashed line to represent our intermolecular forces because they aren't as permanent as a bond would be. When molecules in a liquid are moving around, for example, there are lots of intermolecular forces that are broken and new ones that are formed as the molecules move. Now, the hydrogen bond is the next type of intermolecular force that we'll look at, and it's the strongest of the three intermolecular forces. It's the most specialized as well. And there are two very specific requirements in order for us to be able to have a hydrogen bond between two molecules. The first thing that is needed is a slightly positive hydrogen atom. And this must come from a dipole. So there must be a polar bond within the molecule where hydrogen is left slightly positive. There also must be a lone pair of electrons on a neighboring atom. And that atom must be either oxygen, fluorine, or nitrogen. So let's look at an example here. We've got a water molecule. Water is bent with a lone pair. If I want to look at the intermolecular forces, I need to look at two different water molecules so I can examine the forces between the two. Now, what we have here, if we check the polarity of this bond, is we've got a slightly positive hydrogen atom. So there are dipoles, and I could draw dipoles on all four bonds. Let's check that we've got the requirements of a hydrogen bond. The intermolecular force occurs between a slightly positive hydrogen, so we've got that, and a lone pair of electrons on a neighboring oxygen, fluorine, or nitrogen. So what we have here is a slightly positive hydrogen, and that slightly positive hydrogen is going to be attracted to this lone pair of electrons on the oxygen. And that's where the intermolecular force will be. So the intermolecular force is between this lone pair and this dipole. Okay? And there are the possibility of two separate intermolecular forces because there are two lone pairs. Now, this type of intermolecular force is much stronger than the dipole-dipole force because rather than it being the attraction between a slightly positive to a slightly negative, as it is in a dipole, we've got a slightly positive to a negative from the lone pair of electrons in the oxygen. So therefore, this is a stronger attraction. Now, when we have hydrogen bonds, not only do we have the possibility of establishing this kind of an intermolecular force, the water molecule is still polar. So it is possible to also have dipole-dipole interactions between these two molecules, which again increases the overall intermolecular force. Let's look at NH3. Okay. NH3 is also tetrahedral. It ends up being pyramidal in its geometry because of the lone pair of electrons. And when we check the polarity of this bond, we see that hydrogen is slightly positive. So not only can we just look at this NH3 and say it's a polar molecule because of the lone pair, so it probably has dipole-dipole, we want to look even further to check whether or not hydrogen bonding is possible, because we know that hydrogen bonds are even stronger than the dipole-dipole forces. So what we have here is a slightly positive hydrogen, and we've got a lone pair on a neighboring nitrogen. So the attraction is going to be to the hydrogen, and that's where the hydrogen bonds are going to be. Now, the strength of these hydrogen bonds has actually led scientists to redefine hydrogen bond, because most intermolecular forces are thought of as being non-permanent and quite weak, but the hydrogen bond, as it's studied further, is showing that it actually does have significant overlap between the orbitals of the molecules, and it is much more like a covalent bond than other intermolecular forces. Now, the two types of intermolecular forces that we've talked about so far, the dipole-dipole and the hydrogen, have applied to polar molecules. The third type of intermolecular force, which is London dispersion forces, applies to nonpolar molecules. Now, all molecules will be able to exhibit this type of force, London forces. However, for nonpolar molecules, it is the only type of intermolecular force that they will be able to exhibit. And these are pretty weak. Now, what we have to remember is that we've got a nonpolar molecule. So if I were to look at this molecule, there's no charge separation. So there's no slightly positive side or slightly negative side like there would be in a nonpolar molecule. What can happen, though, is through polarization, we can form an instantaneous dipole. An instantaneous dipole is formed because the electrons within the orbitals in the molecule are randomly moving around. And it's possible that for a moment in time, enough electrons will gather in one area to leave one part of the molecule slightly negative. That will leave another part of the molecule slightly positive. The effect on a neighboring molecule is that the electrons in this molecule will repel these electrons, and so we'll end up with a similar charge separation where we've got a slightly positive and a slightly negative end of the molecule. The formation of these instantaneous dipoles will lead to the possibility of an attraction between the two molecules, and this attraction is the London force. Now, this intermolecular force is quite weak because as quickly as it's formed, it's going to be broken. As quickly as these electrons end up in one area leading to this charge separation, they're going to repel one another and, as a result, break the intermolecular force. So these are referred to as instantaneous dipoles. And also, sometimes they are called momentary dipoles. And that's what this is here. This is the momentary or the instantaneous dipole. Now, in order to decide what type of intermolecular forces will be exhibited between molecules, you first need to draw the three-dimensional structure and decide the polarity of the molecule. Once you've got that, you can decide if hydrogen bonding is possible by deciding if it meets the very strict requirements of having a slightly positive hydrogen and a lone pair on either nitrogen, oxygen, or fluorine. If it can exhibit hydrogen bonds, then you know that all three types of intermolecular forces are possible. So if you're asked for a list, you would list all three. If you're simply discussing the intermolecular forces of a variety of molecules for point of comparison, and one of them exhibits hydrogen bonds, you could just discuss the fact that it has hydrogen bonds, because it is known that if it has hydrogen, it has the other three. If hydrogen bonds are not possible, you would then look at whether the molecule is polar or nonpolar. If the molecule is polar, it will exhibit dipole-dipole and London forces. If it's nonpolar, then London forces are the only intermolecular force that is possible.